there's kind of this new paradigm emerging, this masked diffusion model thing. Basically making diffusion models work with this discrete task, but specifically using it to do discrete next token prediction or discrete token prediction. And in this case, specifically on text. So why might you want to do that? This paper shows that, well, it scales just as well as autoregressive models. Well, it kind of scales as well as autoregressive models. The scaling laws are similar, but it has some nice properties. So one is that it breaks this reverse cause or this reverse curse. So if you've probably heard of the reverse curse in I think that's what it's called in text modeling, and this apparently fixes it, and it makes a lot of sense why it does. So basically with masked diffusion models, you don't need a mask on attention, and you're treating it as a model that is somewhat like diffusing tokens. You can kind of think of it that way for now. And in this way, since you remove the autoregressive mask, you are able to do bidirectional, like tokens can talk to each other both forward and backward. So like normally if I have two tokens, we'll say A and B, and I create this attention mask, or I create the attention matrix here. In a normal autoregressive model, I would mask out this part here so that token A can only attend or token B can only attend to token B, and token A can attend to every token. And this way it's causal. So like if A is the word the and B is the word cat, then A can attend to B, but B can only attend to itself. And the output you get, like A prime is equal to some value of A, and B prime is equal to like A and B. So obviously it's causal. You have A and B. A B is a combination of the past and itself, while A is only a combination of itself. Normal autoregressive behavior. So the problem is you can't send information backward. So like there's no reason during inference why B shouldn't be able to talk with A. The only reason it can't is because it's trained in this autoregressive way because this mask is here. Like during inference, if I have token A and B, or if I have token AB and I want to predict token C, so let me just expand this here. Then, and I'm going to create the mask. So, and if I had another token here, just so that there's more. So if I have tokens A, B, and C, and I want to predict tokens D, and I want to predict token D, basically A and B can send information to token C, but C cannot send information back to token A or B. So C has to collect all this information just to make a prediction about token D, and it can't send any information backward, so you only get this one directional communication. And this is a big problem because it can't do any reverse tasks. Any tasks where this token has to communicate with this token specifically and send information over there. And we'll see later in the experiments that like if you just remove this mask here, then it can do that. The reason you can't just remove the mask in autoregressive modeling is because you want to have this training efficiency. If we say remove the mask in autoregressive modeling, like you can remove the mask in autoregressive modeling, it just becomes inefficient. Let's say I have tokens A and B, and I remove the mask here. So we have this full rank attention matrix here. This means A is a combination, like A prime is a combination of A, so C1A, whereas C1, C2, C3, and C4, plus C2B, and B prime is equal to C2A plus, C3A plus C4D. So this is fine. What we want to do with this is we want to predict the token C, and we want A to predict the token. So we want A to basically predict token B, and we want B to predict token C in some way. Now the problem with this is A now has information to token B, so this is trivial. This is trivial for A. A can super easily predict token B by just saying C2 is equal to 1 and C1 is equal to 0. So this is a problem. And this is why you have the mask. If you have the mask, then it's not a trivial problem, and A has to actually do something to predict token B. That should be a B. Same thing with B, like if we add another token C. So this is why you have the mask. It's so you can have L predictions. So if L is our sequence length, you have a prediction for every token in your sequence. But if you remove the mask and you still want to do autoregressive modeling, one forward pass gives you one prediction. But if you have the mask, doing one forward pass gives you L predictions. So basically, removing the reverse, like doing L forward passes is totally not worth it to remove the reverse cause. And this is why you just train with the mask. And it's like, whatever, it works good enough. But this method does remove that. So I think this is a really cool thing, and I think it's a really cool research direction just because of that. And on top of that, I think it's really interesting trying to diffuse this. It also decouples it from the sequence length, having this diffusion model, because if we have, say, 4 tokens here, and we have our diffusion model here, there's nothing stopping me from doing a one-shot prediction where I take all these tokens, I throw it through the diffusion model, and the diffusion model predicts all these tokens at one time. Like and that's better than your autoregressive model, because the autoregressive model would have to predict token 1, token 2, token 3, and token 4. And there's some ways to kind of speed that up with like speculative decoding and stuff like that. But it's not built into the model directly. So if we really wanted to, we could just have our diffusion model predict every token at once. So it decouples it from the sequence length, which is also really interesting. There's just a lot of interesting research directions with this model, and that's kind of why I think it's really cool. Anyways, enough with me trying to say this is a cool model. This is a cool method. Let me actually talk about it. So the method itself actually isn't that bad. There's a lot of I think I covered it before, but there was a lot of like probability math and stuff. As you would expect. But it actually boils down to something quite simple. So basically with a normal like image diffusion model, you have a prior, which is your Gaussian. So like z at time 1, we'll say z is going to be or z0 is going to be our data. So this is just going to be sampled from our data distribution. I think they call it p data in this case. So this is just going to be our data. So this will be something like an image in R, height by width by 3 or something like that. Then what you do is you progressively add noise to some time step x at time t, where x at time t is something like 1 minus t. In this case, I'm just going to write out the velocity prediction, or the velocity equation for x at time t, times z0 plus t times z1, where z1 is pure Gaussian. And then you have z1 at the end of your chain, which is sampled from a Gaussian or normal distribution with one variance. We'll keep this variance preserving over here, just because that's easy. So basically, this is just an interpolation between your image here, draw a normal, good old cat, and your noise here, which is just pure Gaussian noise. And then what you do is you train a model to reverse this here by saying, a model, I want you to predict something in this equation. That can be the noise, that can be the velocity, it can be basically anything, but basically some way to reverse this chain. But what you need is a easy prior, so like a simple prior that you can sample from, and a way to map from your, an efficient way to map from your data to your prior, and a way to model the reverse. So where the reverse is your diffusion model that you're going to train. We'll add a theta there. There we go, trainable. So how do we do this? Like this is pretty intuitive with image models because it's kind of been around for so long. So how do you do this with tokens? Tokens are discrete. Let's define a few tokens. We'll do the cats at. I'm not creative. So this will be, I think they call it x at time 0. This will be from p data. So this is our initial data that we have, and we have something over here. And that something is going to be mask tokens. So I'll just draw that out with like red for masking. So this may be like, if we have a vocab here and our vocabulary is like 1 maps to the word the, and 2 maps to the word cat, and 3 maps to the word sat, and 4 maps to the word dog, and 5 maps to the word like mask, or rather the token, the masking token, then this here would be 1, 2, 3, and this here would be 5, 5, 5. So this is a corruption by adding noise progressively, and this is a corruption to a easy prior by masking tokens. So you can kind of see where this is going. We're just going to define a forward process. So from your data to your easy distribution over here. I forget. I think they call it like Q or something. So Z1 or X1 is from Q something, and you're basically you're going to define the forward map as an iterative masking procedure with an increasing probability for masking every token, where each probability distribution on every token is independent from the other. So the probability of masking sat and the probability of masking cat are independent of each other. Like if I mask the word sat, that has nothing to do with the word cat. Same thing here. Like if I add noise to this pixel here, it has no relation to this pixel here. So independent masking of your tokens, and that allows you to find a nice and easily computable forward and backward method. So the forward method is defined over here. Basically, if we define alpha t is equal to 1 minus t, this is kind of like the velocity method over here, or the flow matching objective, and we define 1 minus alpha t to be equal to t. That's just because alpha t is equal to 1 minus t. Then you get your probabilities here, where a higher time step, so t is equal to 0, you basically have, or rather, this is the probability of keeping the token, and this is the probability of masking the token, as you can see here. So at time step 0, you have alpha t has a probability of 1, and 1 minus alpha t has a probability of 0, because we define this as 1 minus t and t. So at time step 0, which is our data, you have 100% like probability of mask, or 100% probability of keeping your tokens, and a 0% probability of or a 0% chance of masking your tokens. And then if we go to the other extreme, at time step 1, we have alpha t is equal to 0, and 1 minus alpha t is equal to 1. And this is saying that every token has a 100% chance of being masked. So in here, x at time t is going to be some interpolation of this. So we may sample this and we may get a mask that looks like this, where this first token would be 5 because it's masked, and this would be 2 and 3. So that's pretty intuitive, this forward procedure. Now, the backward procedure is based off this equation here, or based off this probability distribution over here. It's a little bit of a mess how they define this, but basically it boils down to these 3 parts here. So basically what we want is we want to model, what do they define it as? They define it as Q. So we want to model Q to basically reverse this process. So our model is going to be Q 0t. I think this should be a 0 here. So I'm going to write a 0 there instead of an S. This is going to be our model. Basically what this is saying is that should not be t. That should be an x. Given x at time t, so x at time t is going to be some intermediate masking thing. So that can be this, that can be this. So some amount of masking in our sequence. We want the model to reverse this process in some way. And we're going to have the model reverse this by basically giving us x0, Specifically, this is the ith token, so we can just remove that. Basically, what it's going to do is it's going to predict the, so given every token, it's going to predict the probability distribution for that token. So in this case, we have token 5 that's masked. What it's going to do is it's going to predict the probability distribution of this token, and it's going to say, I don't know, like 50% for the word, or for the word 1, which is the word the, and I don't know, 25, 20 for the word 2, 3, and so on for the other words. So yeah, it's like in a normal autoregressive case, you basically have this token turn into a probability distribution through a transformer, and the transformer says, what should this token actually be? Like, give me a probability distribution over all the tokens in this sequence. I don't know why I erased that. So that's what this is here. And if we define I to basically denote the ith token in the sequence. So that's what this is. We're training the model to reverse this. So given any time step here, given any t, it's going to predict this x0 in the sequence. So it's going to basically predict every token at the same time. I'll show you how to sample later, but basically this is what we're doing. We're training a model to basically predict the distribution that should be here for every token in our sequence. So that's what we're doing. And it's according to this here. So this is saying that the distribution, the reverse distribution here basically has this, which says if a token is unmasked, it should stay unmasked. So this token and this token here are unmasked, so we're going to keep it unmasked. This one here says if a token is, it says if a token is masked, then like at time step t, then it'll stay masked with the probability s over t. And this is kind of, they use this to derive the sampling procedure. And then here, this is basically the probability of unmasking, which takes into account the probability the model predicts. So training a model to reverse this. How do we train the model? So we train the model using this objective here, which is literally just cross entropy, or rather this is a negative log likelihood, but you can just use cross entropy. So basically our loss. So we want the model to predict x0 at any time step. So our loss is going to be equal to 1 over t. So we're going to average over all the time steps of the cross entropy of, so we're going to get the prediction from our model, q of 0 given t. I should probably do this over I. So this will be 1 over, we'll average this. So 1 over how many tokens are in here. We'll say there's L tokens in our sequence. So it'll be 1 over L, the sum, I equals 1 to L of cross entropy of. So this will be the prediction of x0, specifically the ith x0 prediction. So this is like token 1 in our, or this is the first token in our case, but let's say we had 2 tokens. Then this would be the cross entropy for this token and this token in the sequence, and so on. So basically the cross entropy over all masked tokens, L is just going to be the number of masked tokens we have because I defined it as such. So this is x I given xt. So the probability distribution that the model predicts given whatever masked tokens we have. And this will just be the label. So this will be the ith token. So this will just be, what would that be? That would just be token I. I'll just token, or the distribution of token I. I'll just call that the index of like index I. So basically, this would be a distribution. Like here, this would be some distribution over the word the, cat, sat, and dog. I don't think they worry about the 5th token. I think I erased it, but I don't think they worry about the 5th token, which would be the pad token in this case, but it's just a prediction over every word. And then this would be the ith token. So in our case up here, since we want it to predict the word the, it would be just 100% for the and 0 for the rest. So the, cat, sat, and dog. So normal negative log, or normal cross entropy, negative log likelihood, same thing for predictions. So yeah, basically just the average negative log likelihood over the predictions, and the way you train this is by saying, all right, I'm going to sample some random time step. So sample a time step between 0 and 1. I'm going to noise, I'm going to get an xt. So I'm going to noise this to some time step. So this is equal to q at time step t. I don't really know how they denote that. It would be q t given 0, xt given x0. So this is our intermediate representation at some point here. And then we model the loss as this up here. So the loss is equal to the average. This is very shorthand notation. Is not mathematical at all. The average cross entropy over all the model predictions, or over all mask tokens. Specifically, it's over mask tokens. So like if a token is unmasked, that just uses context. We don't worry about what the model predicts for unmasked tokens because those stay unmasked. It has a probability of 1 according to our reverse procedure. So yeah, overall, I think this is pretty intuitive. Forward, corrupt tokens by masking them. Reverse, unmasked tokens by training a model to predict the probability of that token to unmask that token. So assuming we have a model that does this pretty well, so given any time step, it can predict the probability distribution pretty well. We can sample pretty easily. And there's so let me show you how they sample. So I'll show you the results after. But the way they sample is here. It looks a little complicated, but basically you can sample by giving the model the entire sequence and asking, or giving the model the entire sequence and being like, "Ayo, what's the probability of every token in the sequence, or every mass token?" And then just taking the max probability, and you can kind of make this autoregressive. So like if we have, say, 3 tokens here that are 4 tokens, and we'll say these 3 are masked. Let's say we want it to predict the, cat, sat, and mat. So this token here is the word the, which is unmasked, and these 3 are masked. So we're going to throw this through our diffusion model, which is completely trained, and we're going to throw the entire thing into here. So we're going to get 4 outputs. This output doesn't matter. Since this token is unmasked, it's going to stay unmasked. Then what we can do is we can say, all right, so this gives me a probability, or let's look at the max probability. Let's say it says the max probability here. So like obviously this is going to output a probability distribution over our entire vocabulary. But what we do is we look at the max probability for every single prediction. So this will output our distribution, this will output our distribution, and this will output our distribution. And we're going to take the argmax of every distribution. So we take the argmax, and let's say this gives us a index, which corresponds to the word dog. And let's say it has a probability of, say, 0.5. And this outputs the word sat with a probability of, say, 0.7. And this outputs the word mat with a probability of 0.6. Like I said, we take the argmax, and this is the probability of that value. So we take the argmax and the max value on this distribution. Of course, applying softmax. So what we can do is we can take the top 1 prediction. So we can take the top k predictions, and we can say, like it depends on how you're sampling, but let's say we sample in a greedy way. So if we sample in a greedy way, we're going to take the top prediction and only the top prediction. So that would mean we take the word sat. So we take the word sat, and this is now going to be the representation. So we're going to unmask this token, and we're going to change it to the word sat. Like these tokens are still masked here, but this token becomes unmasked, and it becomes the word sat. Then what we do is we do another forward pass, and the second forward pass is going to give us a distribution maybe looking like this. Maybe this gives us the word cat with a probability of 0.7. Maybe the context of sat increased this to the word cat, or made this prediction more confident, but changed it to the word cat for some reason. But the word mat becomes 0.9. Maybe it becomes a lot more confident in this prediction because it predicted the word sat. So then we would unmask this one, and we would then change this to the word mat, or we would take this word, change it to the word mat, and yeah, now we have this. And then we do our final inference. So we do our final step where we get the prediction of cat here. Now, nobody says we had to do this greedily. Like we could have done we could have done two at a time. So we could have taken these two predictions at the same time and got the prediction for the word sat, like taken the top two probabilities and taken the word sat and taken the word mat and use that as our next prediction. So this is the cool thing about diffusion models for sampling text. Like we can do this in a autoregressive, I mean, it's not really autoregressive, but in a greedy way where we sample one token at a time. But we don't have to. If we wanted to, we could have sampled the entire sequence, which was dog, sat, and mat. And if we had one step, we could have gotten all three of these tokens. Like granted, it's probably not going to be the best prediction, but if we really wanted to, we could do it in one step. So we get this trade-off that diffusion models have between quality and speed. Another cool thing is you don't predict you don't necessarily predict in order of the sequence. Like notice how I showed this token being predicted first. You don't have to predict in order of the sequence, which is very nice, because this word here, it may need context of future words to be predicted. So I find that part of the inference procedure very, very interesting. And both these properties are something you don't get with autoregressive models unless you do some weird hacky things with autoregressive models. But that's essentially what this is doing. And this part of the loop, it is basically just your greedy, so predict one token at a time, like I showed over here. And this here is just getting the probabilities and stuff. They have code, which is very nice. So go ahead and check that out. I also have notes here, which I'm gonna send if you're curious. So yeah, that's the greedy sampling. They know here that like during each sampling step from time t to s, so if s is one step lower than t, basically you want to unmask one token. If a token is not masked, it remains unmasked. Otherwise, it retains the masked state with a probability of s over t, or transitions to, or becomes unmasked with this probability predicted by the model, with or becomes unmasked with a probability of 1 minus s over t. So this is where the distribution above comes into play. So that is sampling. So another nice thing about diffusion models is you get CFG, which basically allows you to get a performance improvement for free. And, get a performance improvement. It gives you a performance improvement while reducing kind of the variance of your distribution. So it kind of forces it towards one direction, towards the class you specify, but it kind of minimizes the variance of said class, or of the prediction you kind of get. But there is CFG. Like we all know what CFG is. So there is CFG, just like a normal diffusion model that they define here. So normal CFG looks like this. You've probably seen this formula before for a diffusion model. Basically, the noise prediction given a class. So this is usually your text. We can amplify that, the prediction of that class, by removing like the prediction on null data. So we define this value as basically how much we remove by this omega term, where an omega equal to 0. corresponds to just the normal diffusion model with the class prediction. So normal diffusion model with text prediction, so no CFG. But if W or if omega is greater than 0, then you get CFG, where basically you do 2 forward passes, one with the class, one without the class, and the higher the W, the more of the null class you're removing from the class prediction itself. So if this was, say, like dog, then this would be just the null prediction. So basically it's emphasizing the dog part of the prediction as much as possible because you're removing the null part. That's how I like to think about it. So this is the probability version of this here. So this is using regression. This is using probabilities. So the probability version is similar, but I mean, you can kind of see, you basically have your numerator, which is your class prediction, and your denominator, which is your null prediction. So basically you're removing the null part from the class prediction part in the same way, except this is a distribution. So you're doing it in you're dividing. So it makes a lot more sense in terms of distributions. It's basically decreasing the probabilities in the null class in that way. So this here is your class prediction, and this here is your mass prediction. Basically, what this means is if we have a class, this is going to be our prompt. So if I tell GPT, generate me a picture of a cat, then that would be my prompt, and that would be my class. So C would be my prompt. And you can so that's similar to the prompt in like normal diffusion models. It's just baked into the model we have right now. So this is prompt. C is our prompt, and you get this for free because you train it in a masked way. So you can think of this as some x at time t, where the tokens that are masked or the tokens that are unmasked are equal to the prompt, and the tokens that are masked are equal to whatever you want to generate. So that'll be some number of tokens that you want to generate. So this is some intermediate time step, and this is within distribution of our model because we trained it in this masked way. So our prompt is just going to be the conditioning that we have, and we get this for free by training it with the method above. So here's an example I have over here. So like if we had the cat sat on the mat, exclamation point, this can be represented as 7 tokens. And let's say my prompt are these first 3 tokens. So the cat sat, and the basically we want the model to make predictions on the words on these next 4 tokens here. So we want it to kind of continue this sentence here. So this is our class prediction here. And basically for CFG, like normal CFG, you give it the class and you don't give it the class. So the class prediction would be the probability where we give it class. So the probability with the class prediction. So that would just be a normal forward pass. We take this forward pass, we get predictions for all of these tokens here. And then for our null prediction, we do the probability where the class is masked. So we mask each of these here. And this is our null prediction because, and we only take the probability for these 4 tokens here. So this is the null prediction because these tokens are null and there is no class information here. So this is the CFG equivalent of CFG in a normal diffusion model with regression. So that is CFG. And I find that cool that you get this for free. So let's look at the results. Like I said, this wasn't too bad. It's pretty intuitive. And yeah, if you add CFG, it does better, as you would expect. Yeah, so basically they train I think they use the official GPT-2, and they train the masked model, and they train similar in terms of size. Basically, it does about the same in terms of quality here. So about the same in terms of quality, using the greedy sampling procedure that I showed where you sample 1 token at a time. So same size, same amount of flops, and it does about the same. Like you can't tell me one model is better than the other because it's literally 50-50 right here. So the models are basically about the same. There are some where it does significantly better. The mass diffusion model, like Lambda, it does way better with the same size. While the ones it does worse in, it's only a little bit worse. So that's interesting. That may be because they're using the GPT-2 architecture, though. Like, I don't know why they chose GPT-2. Later, they used Llama once. So it's weird to me that they use GPT-2, but these are the comparisons we have. So I don't know. Take them with a don't take them at face value because they're using GPT-2. Like, it's not the best. That's like the worst transformer you could possibly use. So comparing the mass diffusion model to GPT-2 with less parameters on what do? They do another comparison. This is the official one, I think. More comparisons, and it does about the same here. Yeah. So those comparisons. They do some more comparisons with like CFG and stuff, but these are the main ones with GPT-2. So one thing they note is that it takes approximately 16 times more pre-training time. Mass diffusion models takes about 16 times more pre-training time. So that's the first graph they show, and I think it's good that they point this out. Like they're pointing out the flaws in their model, which usually isn't done in machine learning papers, and they're saying, yeah, it does take more compute. So non-embedding parameters. What is this here? These are isoflop curves. So with the same amount of isoflops, or rather, to get the same amount of validation loss. So like if we look at 2.8 here, and we look at 2.8 here, this is the mass diffusion model on the right, and this is the autoregressive model on the left. Basically, to get the same validation loss, you need more isoflops here for the mass diffusion model, about 16 times more. So you don't get all these benefits for free. It takes a lot more compute for the mass diffusion models to work. So it does similar in terms of performance, but it requires a lot more pre-training time. So something to note. I am guessing that can be fixed because this is so early in development. I'm guessing that that's not that bad. It's not that far compared to GPT-2. So I think after once some more research is put into this, it'll be a little bit better. It's, like I said, really early in development. So the reverse direction. So basically, so they say, yeah, they introduce the concept of the reverse curse, which refers to the difficulty of arms in generalizing bidirectional relationships because it cannot, it's impossible. You have the mask there. Specifically, this occurs when a model trained on information in the form A is B fails to infer on B is A, which is obvious because you have the mask there, so it's going to do that. So you get a 0% accuracy score for GPT-2 and Llama. And the mass diffusion model does not get that because it does not have that mask there. So yeah, that works. One thing they say is that this fixes, or at least it does better with temporal quality degradation. So basically, this is, or rather, I'll talk about the setup first. So to evaluate the impact of temporal shifts, they train ARMs and MDMs on the Slim Pajama dataset, so specifically the 2023 version, released 2023, and test them on the FineWeb dataset in 2024, which obtained samples from February and March and April of 2024. So basically, they train on 2023 data, and they test on similar 2024 data, and they show that the mass diffusion model does better. Now, this one I'm a little skeptical about. I don't know, it does do better, which is weird. Whether that says that it overfits less to the data, which maybe it does because you're using a diffusion approach rather than an autoregressive approach. Maybe it overfits less. Maybe that's what this says. Maybe it overfits less to the data, but I don't know. I'm a bit more skeptical about this. This part here, the reverse direction is obvious. That's obvious. You get that because it was defined in that. You don't have the mask, so it should do that. This part here, I'm a bit more skeptical about. I don't know why it would do better in terms of temporal quality degradation. But apparently it does. So yeah, that is this paper. I think this is a really cool approach, and I'm really excited to see maybe the future isn't mass diffusion models, but diffusion models or similar things for generating text. I'm very interested in this area of research, and I'm curious if like autoregressive will be defeated one day by a diffusion approach. Diffusion models are all you need. Paper needs to come in 2025.